Alright, so today we're going to talk about the spring mass pendulum as an example of the Lagrangian formalism. This is going to be a problem where you could do it using Newton's laws, but you certainly wouldn't want to because it would get really hairy really fast. So what exactly is this problem? Well, we're basically going to imagine attaching a mass to a spring, but then letting that swing around in 2 dimensions like a pendulum. So it's like a spring mass pendulum. And this is going to complicate things a little bit because not only can it move just in this theta direction, but it can also stretch and compress as well. So this is like a step up from the regular pendulum. And our choice of generalized coordinates is going to simplify the problem, however. So the coordinates that we're going to want to use is that theta angle and some coordinate s, which we'll call its displacement from its equilibrium value. So suppose that if the equilibrium length of the string was L, then our coordinate s is going to keep track of how far away it is from this L. So it can go back and forth, and it can also swing in the theta direction. However, when we want to actually put this into our Lagrange equation, we're going to run into some problems because it's very easy to write out the energy of the system in terms of our original coordinates. So if we go back and see that if we originally described everything in terms of x and y coordinates, so x right here and y right here, then it would be really easy to write out the 1/2 mv squared. Now, you've got x and y, so to write out the kinetic energy, it'd be 1/2 m x dot squared plus y dot squared. But we want to express this in terms of our new coordinates s and theta. Because since those s and thetas are linearly independent, then that would be the minimum number of equations that we need. Because we haven't gone over what the problem is with if you do have linearly dependent coordinates like x and y, but you basically run into problems really fast because the equations that you get, those Euler-Lagrange equations, aren't independent, so you have to do something special to fix that. So we need to work on getting this kinetic energy and this potential. We need them to be independent of each other. So we need we need our coordinates to be independent of each other. So we're going to need some transformation that's going to turn x's into some function of s and theta, and our y's into some function of s and theta. So if we look at the geometry of our situation, we can actually get the transformation equations fairly easily. So if we look at our x direction, so we're trying to write this in terms of s and theta, then just from trigonometry we can pretty easily see that it's going to be s plus L times the sine of theta. And in a similar manner, y is just going to be s plus L cosine theta. So, because our kinetic energy is dependent on x dot and y dot, not only do we just need these x and y's, but we're also going to need x dot and y dot. So if you take the time derivative of this equation, you get x dot on the left side, obviously. But then on the right side, you have to use product and chain rule. So for the first step, if you differentiate this part right here, then you get s dot sine of theta plus, and the second part you leave this part alone so that L plus S stays alone. And then you would differentiate sine of theta with respect to time, because theta is a function of time. So you differentiate that outside part first, so you get cosine of theta, and then multiply it by the derivative of the inside, which would just be theta dot. And for a similar argument, you get that y dot is equal to s cosine of theta minus L plus S sine of theta, theta dot. Now these, we can plug back into here. And doing it this way is kind of the brute force way. After you do quite a few problems, these become a lot more natural, and you can kind of write out this directly. But I don't feel like we've built that intuition enough yet in this series, so for the first few problems that we do, I'll be doing this procedure where we write out our energy in terms of the easy coordinates, kind of like what we have up here, and then use some transformation to give us our energy in terms of the generalized coordinates. So that's why I'm doing that in this video. So when we plug those x dot, y, and y dot back into our equations, we get that t is equal to 1/2 m s dot squared plus L plus S squared theta dot squared, which, if you look up here, that x dot squared plus the y dot squared, if you look at these terms right here, whenever you square them, you get an s dot squared sine squared theta, and then you'll get a 2 times this plus this, but then here you're going to get a negative 2 minus this times this, so that'll cancel. And then you'll have L plus S squared cosine squared theta L plus S. And then when you square that y dot and then add it to this, so this is going to contribute a s dot squared cosine squared theta, which you could combine with this one to just get an s dot squared. And then here you would get a contribution of this thing right here, but just with sine squared theta, so you can combine that as well. So that's how you get this part. And luckily the second part is a little bit easier, because we're just plugging in y, so that negative mg L plus s cosine theta plus 1/2 ks squared. And the reason our potential has that minus sign is it doesn't matter where we set our 0 reference point. So we set it to 0 at the top, so that to fix, because we usually think about measuring potential from like some ground position, and our potential increases as we go up. But that's the same thing as if we set it 0 right here, and we set the potential to decrease with increasing y in this direction. So it doesn't matter where you set your reference point, as long as potential still goes up and down in the same manner. So in a constant gravitational field, your potential should increase with increasing height, and your potential should decrease with decreasing height. So that's why we have that negative sign out right here. So that when y gets bigger, our potential gets smaller. Alright, so now we're actually ready to plug this into the Euler-Lagrange equation, because our Lagrangian, like I said in the last video, is going to be our kinetic minus our potential. So there's the kinetic term right here, and here's the minus potential term right here. And then whenever we plug these into the Euler-Lagrange equation, so in general, our Euler-Lagrange equation look like d over dt partial L over partial q dot minus partial L over partial q is equal to 0, where q is going to be a generalized coordinate. So here, this is like the general form, but now we actually get to plug in actual coordinates in for this equation. So for example, for each generalized coordinate we have, we get to plug it into the Euler-Lagrange equation, since they're independent of each other. So we have that d over dt partial L over partial s dot minus partial L over partial s, and a similar situation for the theta direction. So whenever we take the appropriate derivatives, we get these coupled nonlinear differential equations. Now, I stated that the Lagrange method was easier, and what I mean by that is that it's easier to get the differential equations of motion. So if you can write out the energy of the system, you can get the equations of motion. But then to actually study the equations of motion is going to be a different story. And that's the same thing with Newton, and the only way we're going to fix that is in another formalism called the Hamiltonian formalism, but we won't get that for quite a while. So just know that if you want the equations of motion, then you want to use Lagrange, because if you can write out the energy of the system, you can take a few derivatives, get your equations of motion. But if you want to thoroughly look at a system, then that's whenever we're going to have to switch to the Hamiltonian formalism. And in the next video, I'm going to go over general properties of the Lagrangian formalism to get a better sense of what we can do with this formalism. So I hope that you liked this video. Let me know if you liked it in the comments. See you in the next video.